talking about diversity of core collapse supernovae. Okay. Are we ready to roll?
Yes.
Great. So, I missed, I guess maybe one of Avishai's first talks. But just talking to people who were here, I thought it would be good to do two things this morning. One is a little bit more on type 2p supernovae. Udi did a great job. Where's Udi? Okay, if he's not here, that means I can give the talk without an argument. Udi gave a great talk on explaining the light curve, rough light curve. So I'm going to show you. Oops. Sorry. I knew something was missing. Udi summarized the type 2p light curves quite nicely, and I'm going to sort of go one step further and talk about how the analytics that were done by a few different groups really does compare quite well to what you get from a numerical calculation. And I'll also talk about the diversity of those supernovae. The type 2p supernovae are the most commonly observed core collapse supernovae, but within that class there's a tremendous amount of diversity. And I want to highlight that because the hopes are that that diversity will start to tell us more about the diversity of outcomes of the core collapse events themselves. So I'm going to first summarize that. And then I'm going to talk pretty much solely on one class of the superluminous supernovae, those that are typically 100 times brighter than the type 2Ps, and for which Dan and I and Stan Woosley independently have been working on the notion that these are caused by the birth of a rapidly rotating, highly magnetic neutron star that we often refer to as a magnetard. So I'm going to start with typical core collapse supernovae. So again, just to set the stage, and I think it's also never hurts to see things twice. So if we've already talked about this before I arrived, sorry, but seeing it twice doesn't hurt. So these are what we call the type 2p supernovae. I'm not going to show you any spectra. Dan's going to do that, I'm confident. He's grinning. That's good. Okay. But the spectra of a type 2p is type 2 means it has hydrogen. And what you see during the first 100 days is that hydrogen, and you see it in p Cygni lines. But these are what the luminosities look like. So there's a period of nearly constant in astronomical sense, which means within a factor of 2. Luminosity, a clear transition to then a tail, which is powered by the radioactive decay of the nickel-56 that was made deep within the supernovae. And so what I'm going to talk about is how we understand this luminosity, going a little bit slightly one step beyond what Udi did, and then also highlight how we use those observations to infer things. For example, the explosion energy, the radius of the star, and potentially the mass that was ejected. So why is this an interesting thing to do? Well, all of the surveys that are happening, and of course they just continue to go, the observers keep finding a lot of supernovae, are such that the data set we have for the type 2Ps is extremely rich. There are hundreds of these for which there's detailed light curves. And as someone who pays tax money to get that data, I would like us to actually get something out of it, like what was the explosion energy, what was the mass. And so that's sort of my approach to this problem. But the other reason to do it is that we see these in distant galaxies. As already commented on by Avishai, it's often the case that you have a pre-image from HST of a galaxy, and then later you find a supernovae. And those pre-images are being used to infer the mass of the star that exploded. And so you should ask, does the mass of the star exploded agree with the mass inferred from the modeling of the supernovae? I'm not going to answer that because we don't know the answer. That's a little bit embarrassing. So this is another plot. Avishai didn't really show this, but this is just from one of the review articles by Stephen Smart of a summary of the progenitors in nearby galaxies. So these are HR diagrams of different mass stars. The black circles are where progenitors appeared in distant galaxies for type 2p. And the mass, as I'm going to talk about, is inferred by basically which star can reach this point. And so typically keep in mind that the objects we're seeing as progenitors are 20 solar mass or so. They are red supergiants. And the red supergiant problem was sort of discussed a little bit. Whether there's a problem or not, we'll see. I think it's still kind of early days to really infer that. Some objects called type 2b's we know have reduced their envelopes, and so indeed they're sitting at more of a, as what we'd call more of a yellow supergiant than a red supergiant. But this is sort of the status of this, and this is only going to get better. So I'm going to pause and see if there's questions on this plot. I'm not sure. Was this shown before? No. Yes? No? Nobody remembers? That's a no. Okay, good. So any questions on this plot then? Because this is kind of, this is the game that's going to keep getting played for decades.
So are the 10 solar mass progenitors convincing?
Yeah, I think so. I think some of those are, one of those is one of the better ones. I don't have the table with, some of these are really, really quite good. Yeah. Yes?
There's a stellar evolution track is from which group?
This is from Eldridge and Tout. Yeah. That was what Smart used. Yeah, thankfully. That's a good point, Sterl. That's right. So if, that's right. We expect a factor of 2 in ejected mass. Remember, from theory, we think, I think it's a fair statement, we think that the lowest mass star that can explode is probably around 8 to 9. I don't know. Somebody did stellar evolution day 1, right? Didn't you do something? You said 9. Okay. Stars below that make white dwarfs. There's a range of making oxygen, neon, magnesium, which I talked about a little bit, or hinted at, between 6 and 9, and then 6 and lower are all things that are 1 solar mass or less and are CO. Okay? And of course, because of the initial mass function, there's many, many more at 10, 11, 12 than there are at 20. Okay. So, how is the game played? The game is played the following. I see an object sitting here at a luminosity of 10 to the 5. And you can't see it because the tracks are hidden. But a 12 solar mass star cannot get that bright. Okay? It's kind of hard to see in this plot, unfortunately. And so what's done is, using a stellar evolution code, you calculate what's the luminosity of the star that the code tells you it should have at the moment you're sort of done with burning. So typically it's carbon burning is the point that's used. And so you can make a plot of the final luminosity versus the initial mass. And this is what was in SMART. And then here's, this had the Eldridge and Tout, the Geneva code and Kepler, and then Matteo was nice enough to run MESA. So there's not really much disagreement. But it is important to show this because everything I'm talking about is basically stars between 4.7 and 5. And you go across and read off the masses. That is how this is done. Okay, this is state of the art.
Is that reliable?
Well, you'd like to test it first. So I think we haven't, I think it's something that we should test, right? So we need to test it by measuring an ejected mass. And I'm not going to give you the answer today because we don't have, I would say, ejected masses with error bars yet. Okay, so unfortunately I can't answer your question yet. But that's the only way to judge the reliability. Right? We don't have other ways of measuring these masses. So it's also important to keep in mind, I should just say it out loud, most massive stars of this mass range are binaries. So these apparently are there's some that are, there are none that are isolated. But these are obviously objects for which, as far as we can tell at the time of explosion, if they were in a binary, then a very wide binary, they became a red supergiant. Okay, so we're testing the presumption here is we're testing single stellar evolution. If some of these had a tremendous amount of mass transfer and it's one system that still became a red supergiant after mass transfer, that's a different theoretical calculation that I don't have here. Okay? So that's another issue about the reliability.
Lars, what would
Yep.
be the derived masses of the progenitors just before the explosion? For 10 Zars
Yeah.
mass,
That,
it will be something like 9, right? They don't lose a lot of mass.
Right, that's right.
If they explode as a 2p or 2p.
Yeah, typically the ejected masses we're going to talk about are 10 to 15. So, but that's the sort of the presumption when we blow the stars up, that they haven't had a lot of mass loss. There's a lot of metallicity variety in these galaxies, but these are not such massive stars that you lose a large part of the envelope. So yeah, mass loss is an uncertainty, but it's probably not a factor of 2 in the ejected mass. But we'll find out. Yeah. Okay, so what are the punchlines? Oh, yep.
It has a comparison study by St. John's, which shows quite diversity between like Mesa, Kepler, and Geneva.
Sure.
I mean, for location on the
That was a result for this plot you're showing? For this?
yeah, I can't believe it.
Yeah, you hardly believe it. Okay. So, so another variable, let me just give you all the uncertainties. Another variable is the amount of overshoot you presume there has happened on the hydrogen main sequence. That makes a larger helium core. If you have a larger helium core, you are a more luminous star at the time of explosion. Okay, for sure. So, yes. Yep. Okay, so what's the current punchlines if you're from, and again, I'm highlighting Stephen Smart's review article. At least back in 2015, there were 18 of these, which is more or less what Avishai was showing us. As I already highlighted, the evolutions and outcomes are expected to be from single star. But we do know from this data that 2Ps are coming from red supergiants, again, which is not a surprise. This is the mass range. And this is going to be important for explosion modeling. And we also know that the radii of these are ranging across this range, 500 to 900 our sun. Okay? All right. So that's the summary of what we know about the progenitors. So now what I'm going to do is launch into our current understanding of the light curves from analytics and numerical modeling with many different codes. So first, let me just start to set the stage with what's happening within the star. So all of the stellar modeling that's being done of these explosions has different ways of injecting energy deep in the core. So these are not calculations that are actually calculating the core collapse itself. They're going into a stellar model and putting energy or a piston deep down into the star of a certain amount of energy that's put in by hand so as to explore the diversity of the energy. It's a free parameter. Same goes for the amount of nickel. Okay, the amount of nickel that's injected in the stellar modeling is a free parameter. Those, of course, are the things that we'd like to use the observations to tell us what are those parameters, so we need to explore that diversity. So one part of the physics problem is just evolving that shock wave through the red supergiant core and envelope after the energy has been deposited. So this is a plot from the fourth MESA paper that just came out, showing the evolution of the velocity of the fluid within a red supergiant as a function of time from the energy being deposited. And in this case, it was nearly 10 to the 51 ergs was deposited. So what's shown here is as a function of time at 36 seconds, this is the mass coordinate within the star. This is the velocity of the fluid. This is where the shock wave is at 36 seconds. It's, as it progresses, this is the helium shell, this is a hydrogen envelope. You can see as time progresses, the shock wave is moving out. So at, let's say, 20 hours, it's not yet at the surface of the star. This is where the shock wave resides, and this is the outward velocity of the fluid. Okay? This dashed line is the analytics from Matzner and McKee of what you would expect. It was updated by Jonathan Tan in a separate paper. What you would expect for the post-shock velocity of the fluid when it's at this coordinate. So the fact that the numerics agrees with the analytics here is actually quite striking. So I don't think we have any worries about the ability to run a shock wave through a radiation-dominated plasma. And Matzner and McKee were quite happy to see this plot, I can tell you. But let's stare at this for a moment just to give a sense for what could be some puzzles. So first off, if I'm a fluid element, let's say I'm right here at let's say at 10 solar masses at this point, at a time of 20 hours, I'm moving at this speed. You can see at a little bit later, I'm actually moving slower. Right? That's this line. So all of these fluid elements are suffering deceleration. right? They're suffering deceleration basically because the shock wave has yet to depart the star, okay? Those decelerations, especially here at the hydrogen-helium boundary, lead to Rayleigh-Taylor instabilities, which I'm not going to talk about at all today, but that leads to mixing of the ejecta deep in the interior, and that happens in multiple locations, and that's one cause for both hydrogen and helium mixing, but also lets nickel, if it's sitting in the metals due to asymmetric injection of nickel-56 in the core, if you seed it at this point, the Rayleigh-Taylor can then bring the nickel out, and that is something that has to be thought through. Okay, so let me stop and see if there's any questions on this plot. Yep. Sorry?
What caused that jump in the velocity?
This jump?
The dashed line.
This dash line?
The peak,
Oh.
this peak.
Oh, this is the hydrogen helium boundary. So this knows about the density profile. So there's a very sharp density profile. And that's the cause of this peak and the predicted the evolution of the shock. So the shock, as you can see, rapidly decelerates as it goes down this. Okay.
So with the outer parts, the density profile is shallower than hydrogen.
Yeah,
That's why you see
yeah, a little bit. That's right. It's a little bit shallower.
where is the,
I don't have the rho RQ plot. Sorry, I should have it, but I don't. Yeah, I mean I have it, but I don't have it here. Yeah, it's a fair question. Yeah. The dashed line is the analytic prediction for when the shock reaches that mass coordinate, what should be the post-shock velocity. And so that's this dashed line, is the prediction, analytical prediction from Matzner and McKee. And so this is just showing that indeed the hydrodynamics, and this is what's within MESA, agrees with the analytics. I mean, we, you know, as part of what we do within the MESA code is we compare everywhere we can to anything available. Analytics, other numerics, because people are going to use this code.
so the envelope is beyond 15 solar mass.
No, this is the envelope here. This is the
Yeah,
envelope.
the,
This is the surface of the star right here.
okay.
That's the surface.
So it starts to accelerate beyond 10.
Yeah, right. It's right here. It's the surface. Yeah. Yes? Oh, that's a whole separate talk. Yeah, that's a great question. Oh, yeah, what determines the amount of mixing? It's time-dependent Rayleigh-Taylor instability. So how long you're decelerated really matters. So it'll be different in a red supergiant than in a blue supergiant. It'll depend on the amount of hydrogen envelope. So there's a whole study there that there's not a simple answer. But we think we know how to at least start to talk about it. Yeah.
What is the cause of the acceleration?
This is basically a reflection of the density profile within the star. So this is the steep gradient right near the surface. The density gradient right at the surface of the star gets extreme. And so that's what you're seeing in terms of the acceleration of the post-shock velocity. And indeed, you know, the whole surface of the star is a different problem when you do shock breakout.
It was always the same thing. It's like pitches the helium boundary.
Yeah, right, exactly. Right here's the same thing. This is the collapse from, you know, if I showed you the density profile, there's a huge collapse in the density between the helium core and the hydrogen envelope, and that's the cause of this acceleration.
And during that time, the posture fluid accelerates by this factor of 2. We will do that many times, and you see a little bit of that in the left side of this figure. But then when it hits the envelope, which is still more massive, because most of the mass is actually in the envelope, the shock decelerates, and the posture fluid also decelerates.
People love this plot. It's good. It's actually in Matzner and McKee, but it's not as pretty. Okay. So what I want to do is sort of just remind everybody of what Udi already showed us. If I now just do a rough calculation of that hydrogen and helium envelope is the major part of the mass, what I don't show you is the post-shock temperature, but all the energy is indeed in radiation for these cases. Then I just let that expand as a function of time, and I can calculate different aspects. So for example, as Udi already highlighted, as this ejecta expands, there's a local diffusion time through the whole envelope, And that will scale simply as kappa m over RC, or R now is not the radius of the star, rather this is the ejector radius, so this will be velocity times time. And there comes a moment where the radiation diffusion time equals the age, and that's what defines this characteristic time scale that Udi derived, which is the kappa m over VC. And for these types of objects, it's 10 to 20 days. And so before that time, this material deep in the star is just undergoing adiabatic expansion. So you want to think of this ejecta as radiation's trapped is expanding in radius. As it expands in radius, the material deep within is just undergoing adiabatic expansion. Well, some of you have taken cosmology, and you probably remember that adiabatic expansion just means that temperature goes like 1 over R, which is again what Udi derived. And so the temperature evolution of the ejecta deep within it, if there's no extra heating from nickel, will just go like 1 over the radius of the ejecta at that point in time. So let's look at a model. So this is some nice plots from Utrobin's paper on 99 EM. So again, these are the mass coordinate within the ejecta. This is the density. And so this is the hydrogen-helium envelope. This is the helium core, in his case, at different times, so 10 days, 20 days, 40 days. And he's showing where is the photosphere in this model at that time. So you see at 10 and 20 days, it's still right out near the very surface of the ejecta. And as time goes by, the photosphere moves in. So at 40 days, I've moved in about maybe 1 solar mass. Here's 60 days and 80 days. And this is the temperature profile within the ejecta. Okay? So it's a little bit hard to see here, but basically if I go from hopefully 10 to 20 days, I haven't checked this. Actually, we should check adiabatic expansion. Here we go. Everybody ready? Okay, so if I go from 10 days to 40 days, right, everything should be how much bigger? What factor? Coffee's kicking in? Not yet? 4 times bigger, right? Thank you. 4 times bigger, right? So let's check. So deep within, so down here, this material is optically thick, right? Totally optically thick. So between 10 and 40 days, that's a factor of 40, right? Are we seeing a factor of 40 decline in the temperature? 4. Sorry, thank you. My coffee didn't kick in. All right, factor of 4. Yeah, it looks pretty close to a factor of 4, right? This is a log plot, right? If I go from 10 to 100 days deep within, I've got to be a little bit careful because he probably has nickel in here, so I don't want to go there, okay? So you can also see as the photosphere moves in, the photosphere is locked in at this point at a temperature which is having to do with the hydrogen recombination, which again, no, tau of 2/3 is his point. This is tau of 2/3 for him. Thank you, because I was about to highlight the other point, which you're hitting me perfect. Look at this. Look at this region. This is exactly what you just asked. Here is tau of C over V. Okay? So what you're seeing is that this is a atmosphere. I do stars. Okay? That's what I do. This is simple. We know how to do this, right? I have a bottom boundary condition at a finite temperature. This is in radiative equilibrium above tau of C over V. And so I know what the luminosity is, and that's what Udi showed. Udi is back there. He's even waving at me and smiling, I think. Okay? But that's exactly what you're seeing here. Okay? And you can see it. I mean, here it is. It's always there. Right? So that's why I wanted to show this plot. It's very rare to see these plots, by the way. It's hard to find them in the literature. Okay. Any questions on this? Yes?
There is spike in the temperature.
Oh, I cannot speak to what, this is not my calculation. I can't speak to this, but this is likely just due to poor resolution at the surface. Most of these ejecta full calculations don't get wrapped up in handling the surface of the star that well. There typically is a bifurcated efforts for people. So, but now this is a beautiful thing for the C over V. I mean, that's why I showed this plot. Okay, so what Udi talked about is that there's an optical depth as you go into the object. There's an optical depth you have to get to so that the local diffusion time at that location is longer than the expansion time. Outside of that, the diffusion time is short. And so you just want to think of it as if the diffusion time is short, then it's just going to respond to some whatever temperature I've got at the floor. So if I invert it, because it's easier this way. So I have this location where tau is C over V, so that's whatever, 100, optically thick. Above that point, the temperature profile is just going to be a temperature profile of nearly constant luminosity. It's just carrying heat, and the temperature has to decline. And so it's in local radiative equilibrium at the luminosity, and that's what you see. That's why there's a gradient here. Okay. And the rest of this is just the adiabatic temperature decline as a function of time. Okay. Is in this, yeah. If I go into a star and it has constant luminosity, the temperature just keeps rising. So, yeah. Yeah, it's too bad he didn't mark C over V on this plot. We should make this plot, and Jared, we should make this plot. Yeah. All right. Any more questions on this? This is a nice plot from Desart and Hillier for their calculations. This is a 15 solar mass model. Again, this is time since shock breakout. What's being shown here on this axis, which is why I like to show this plot, is they're showing the mass above the photosphere. It's sort of what we could also read off of the plot from Utrobin. But you can see at early times, 10 to 30 days, the mass above your head is pretty small, 0.1 to 0.01. That's why the early light curves can be modified by circumstellar material. So there's now a major industry, observationally and theoretically, which I'm not going to really talk about at all, of putting material outside of the star to screw up the light curve, as I like to say. And you can do a lot of damage if you add 0.01 or 0.1 or solar masses just outside, and you can do that damage from day 0 to day 30. Okay? And that's just if you change the density profile for that material, you'll get a brighter supernova at early times. By day 50, you're into typically a mass coordinate 2 or 3 solar masses within the ejecta. And so the hope is eventually you're in the star. Okay? You're in what was the star. What's also shown here is the abundance of elements. So this is showing that you're in the hydrogen-helium outer envelope. Then you see the helium shell eventually, and then eventually you get into the metal ball, the core, and then you're done at this point. This is showing the hydrogen abundance. So there's mixing in here by hand. Is this mixing? Okay. So if you keep going for this algebra, you can roughly get the luminosity of these objects back of the envelope. Of course, this has been done more carefully, as I'm going to show. But again, the main thing I want to highlight here is the luminosity you expect from these knows about the energy of the explosion, the initial radius of the star, and the ejected mass. Okay? And this works well, which is what I want to start showing. And again, this is a perturbation on what Udi derived. This is the simpler version. Okay. So here's a nice work by Dan and Stan Woosley comparing the actual numerical luminosity of this was a calculation done with a stellar model that was Kepler, but the light curve was calculated via Sedona. So that's a multi-frequency light curve. So this shows the luminosity obtained versus that expected from the analytical predictions by Popov. So to within typically 5 to 10%, the analytic calculation is a good representation. This is the new paper by Tug Suckbold. This is a little bit different. These are Kepler stars built from Kepler, but then also blown up within Kepler, and light curves with Kepler, which means they're gray. So this is a gray calculation. And what's shown here is the calculation found from the code versus equation 15. They should have said Popov, but that's what equation 15 was Popov. And again, what you're seeing is basically that it works pretty well. And there's a rescaling only of the prefactor. So the power laws are frozen from Popov, but you rescale. And the reason this is important is we'd like to be able to use this because with the large amounts of supernovae that are being detected, you'd like to get some initial understanding just from the analytics and then go do the detailed work. Okay, so the luminosity, this is at day 50, sorry. This is always at day 50. That's a pretty good time because, again, you're hopefully away from the circumstellar issues. So I already highlighted this, that during the plateau, it's basically the photosphere working its way through the hydrogen envelope. Popov also did a calculation for how that sets the duration of the plateau. If I have nickel, which I do in most of these supernovae, you can lengthen the plateau as I'm going to show. So this is, again, from Dan's paper with Stan, showing the numerical plateau duration on this axis versus what was predicted by Popov. Again, pretty good. Large dynamic range here. We don't see type 2Ps with 180-day plateaus, but that doesn't matter. This is a theoretical exercise. Okay? This is just a plot from the recent MESA paper just showing what happens if you have the same explosion energy but strip a star down. And again, as you strip it down, you start to get a shorter plateau, as you would sort of expect. So if you want to see, if you want to measure the ejecta mass, this is the way you're going to probably get your hands on it. And the update to this curve, again, remember this is Sedona. This is from Tugg's paper. The plateau duration, again, this is just really just view. This is just different models. But again, they used, all they had to do was just change the prefactor in Popov scaling, and then basically within the error bars, the analytical scaling expected. This is with no nickel and the light curves. The analytical scaling agreed with the numerics. Okay. Just to give you a sense, so this is just a good sort of pedagogical plot of how much damage you can do with nickel. So this is something that's sort of similar to 99 EM. This is again from MESA 4, showing the plateau period. And again, with nickel, you really do prolong the plateau quite a bit. So you can see I'm adding 20 to 30 days. Okay. Of course, you measure and infer the nickel by seeing the nickel tail, and so you have to correct for this if you're going to use any of these formulas. And that's what's shown in this plot. Yep. This is MESA plus Stella. This is MESA plus Stella, yeah. So in MESA 4, we use Stella for the light curves, which is multi-frequency. That's correct. That's correct. Right. I mean, this plot really is just to sort of highlight the nickel. Because again, we'd like to use, right, what we'd like to use is this thing you can measure, which is the time for this collapse to occur, to infer something. And so you have to see how much the nickel can do.
So what did the physics say last? The nickel changes the opacity?
There's multiple things. So one is at late times, so it's really tied up now in the Rayleigh-Taylor instability, unfortunately. So there's not going to be a simple answer. The simplest answer is primarily maintaining opacity because things stay hot is one piece of it, right? I mean, that's the other piece of it is that the material is actually also not just the opacity, but the fact that it's actually just hotter, right? So you don't have as much, you're no longer adiabatic for those fluid elements. So there's multiple pieces.
It seems to me that the shortfall in there is tau equals COP for the whole stuff.
This is still, the sharp drop here is typically your optically thin through the whole ejecta.
Exactly.
Yeah, tau of 1. Yeah.
So that's a change in opacity only, nothing else.
Yeah, primarily it is primarily changing opacity. I don't have those plots. That's the problem. I can't really show you.
And also the velocity.
Well, this is okay.
Change
So
in opacity also.
yeah, so this has to do really with how you're doing mixing deep in the core. So thankfully, at early days, there's no change in the velocity profile, with or without nickel, because the nickel isn't doing much in the outer envelope. At late times, you get to see more, so you can actually measure the velocity deep in the core because you still have a photosphere. But this is where you can see this is the velocity at the photosphere, where in this case, this is defined as the Russell mean of 2/3. So you can see that the photosphere is at a higher velocity when you have nickel. And that is indeed because there's more opacity further out. Right? So you're still out in faster moving material. So that's why there's an offset here. So again, this is you can kind of calibrate this, and this just shows again from Tug's work with Kepler plus Kepler. The light curves you typically are. This is just the correction due to nickel. Don't worry about what this crazy thing is here. This is the best guess at the analytics, some earlier work that Dan had done. But typically, you can prolong the plateau by 20 or 30%. Okay, so it's a big effect. So you have to really do the nickel. Okay. So what I want to transition to is I've shown that explosion energies matter, ejected masses matter, nickel matters. And there is a lot of diversity within the type 2p. And as I already highlighted, we'd like to use that to start to invert this problem. So just to show you some of this diversity, this is just a compilation of a bunch of LCO light curves from Stefano Valenti of type 2p's. So this is just to impress you about the amount of data we have and why I'd say we'd like to get like 3 numbers out of all this, right? But there are some correlations. So let me show you probably the most prevalent correlation that is an observed correlation that doesn't need any. This is not a theory plot. These are now data. So what I'm showing here is the absolute magnitude at day 50. So this is like that luminosity at day 50. Okay. Versus the nickel mass. I'm still showing the one from his draft where he. Versus the nickel mass. So here's 0.1, 0.01. Okay. So remember a factor of 1 in magnitude. So this is basically 2.5 magnitudes of diversity in the peak, the plateau luminosity. Okay. So any student want to tell me what's 2.5 magnitudes by factor? Huh? Factor of 10. So you're also alert this morning. Okay, so we're seeing a factor of 10, easily a factor of 10 diversity in that plateau luminosity. Okay. So I've reminded you of roughly what the ballpark formula is for that. So I'm seeing a factor of 10 at day 50. This is roughly speaking what that luminosity is. So I have to ask, how do I get a factor of 10 in this variable? Okay. If they're all red supergiants, I don't have a factor of 10 in radius. I maybe have a factor of 2. In mass, I've maybe got a factor of 2. And so what one tends to be highlighting for the range of stars that we think are blowing up is that we're seeing a diversity in the energy that was put in from the core collapse event itself. Okay? So you will see plots, as my talk goes on, where this axis, basically, this plot looks very similar, where this axis goes to energy of explosion. Okay? And this is why it's important to have things like that you knew was a red supergiant in a certain galaxy, because you get rid of some of the uncertainty in these other variables. Right? Okay, so then that's quite important, because this then would say, if I translate this to energy of explosion, that the weak explosions make much less nickel. Okay, now why is that not a crazy statement? How is the nickel made? What's one way to make nickel in the event? I don't think anybody's done this problem for you in the last 6 days, but you've had enough to think about. Well, what would happen if I increase the energy of the shock wave? What happens to the temperature behind the shock if I increase the energy? It's going to go up, right? So for very high energy explosions, I have an opportunity to do shock nucleosynthesis, where basically I can convert some of the inner core to nickel 56 directly due to the fact that I'm doing shock nucleosynthesis. Okay? So what I can't tell you, because we don't have a good understanding of the core collapse mechanism, is whether this is the correlation expected, but it's at least has the right slope. Okay? But that's why I wanted to talk about it. This is this diversity of what we're observing. is one thing. So let's start asking about inverting this problem. So this has been done by Peja and Prieto quite nicely. So basically, they've been using 3 different variables: the luminosity at day 50, for which I've given you a formula; the duration of the plateau, for which I've given you a formula; and the velocity at day 50, for which I'm not talking about. And unfortunately, it's because it's right now under some uncertainty. But they took E as 1/2 mv squared, which is not a crazy hypothesis. But if I have 3 formulas and 3 variables, I invert it, and I can get the ejected mass, the explosion energy, and the initial stellar radius. So here we go. So if they use the Popov formula, which I've just shown you multiple times, works pretty well, and you invert this, what do you get? So this is the explosion energy of these. So again, a diversity of a factor of 10 in explosion energy. These are different supernovae. This is just showing you the observational uncertainties given distance, et cetera, et cetera. Okay, so this is the explosion energy inferred in units of 10 to the 51 10 to the 51 is here. Okay, versus ejected mass. So here's 10. So getting back to starting to ask, are we crazy? Well, no, we're not crazy. Here's 10 solar masses, so this is looking okay. And each of these is a separate supernovae. And so there's an update on this paper, but it doesn't really matter for what I want to do today. Here's the plot that is like the observed plot. So now this is the mass of nickel. Mass of nickel is pretty well measured. You measure the radioactive tail, right? You just measure it. So that's a pretty well determined. And again, it's only uncertain because of distance. This is the explosion energy on this axis. So again, as I highlighted, this is the one I just had shown, which would have been peak brightness. Peak brightness. Again, I've got a factor of roughly 30 in this case of explosion energy. And those with low explosion energies make little nickel. Okay. Now the plot they didn't put in their paper, but I asked for it, and they sent it, is the radius. Was it a red supergiant? And I told you what the radii should be, right? 500 to 1,000. So 300 to 1,000. So not bad. Okay. You might worry about some of these. But again, this is sort of early days for this exercise. Okay, so let me pause for a minute and see if there's questions. Yes?
So can you repeat what are the 3 observables
That were used here. So the velocity at day 50 of the photosphere, inferred from the iron 2 line, the luminosity at day 50, and the duration of the plateau. Those are the 3. So for each supernovae in this sample, those are the numbers they inferred. And then the nickel mass is basically a measured quantity. Yeah. 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 Okay. All right. You're stunned. Okay, so the future of this, I'm sort of done with 2Ps. There's definitely a lot more modeling efforts that are going on, just sort of check. So for example, I said that E is 1/2 mv squared is what Peja and Prieto used. That's something that we're actively looking at with Jared Goldberg. And we're going to hopefully just keep doing this. And as I already highlighted, the impact of the CSM is a substantial issue, but hopefully, or typically, doesn't really matter much for what I've just talked about, which is inferring the gross properties of the events. And so ideally, we'll have a nice supernovae, nearby galaxy, good light curves, nice progenitor, and we can answer the question, does the ejected mass have anything to do with the mass inferred from the progenitor, right? Okay. So now I'm going to switch gears and go to different supernovae. So if you have any questions about type 2Ps, last chance. Okay. Yes, please. Okay.
So just to clarify, so you would expect a correlation, like the correlation between the nickel mass and the brightness?
Yes.
You would also expect a correlation between the nickel mass and the data duration, right?
Yeah, but it's weaker. Yeah, it's the major thing that sets the let's go back. So let's go back to the Popov formula. So the plateau duration really knows more about the mass than the energy, right? In terms of what it cares about. But yeah, you're right. I mean, if it's a more energetic explosion, the plateau is shorter. That's this form. That's this relation. That's correct. But it knows more about the mass. So in terms of dynamic range, or maybe that's what you're asking, right? I am seeing a factor of 10 dynamic range here, and probably a factor of 2 here. So in terms of, maybe that's what you were asking, in terms of what gives you, yes. I mean, this can have a comparable impact on what we see, right? And thankfully, it doesn't depend much on the radius.
Show again the Likert from Stefano
Sure.
sample.
Yeah. Forward. Forward, sorry. Yes, you're right. The other forward, right, exactly. Okay, sorry, almost there. There we go.
So here, most of, I want to relate it to the early part,
Sure.
the beginning of the plateau. So here, really, for most of the objects here,
Yeah.
you see that there is no early bump that is brighter than the plateau. And that's like the typical 2Ps, right? There is a quick rise and settling immediately on the plateau.
In this color, that's correct.
Yeah.
This is a good example, I think, of what you're asking. That's correct. So but there's many that show a little hiccup here.
But I want to ask you about,
Top right has a little one.
but you mentioned
Okay,
about
wait.
this whole industry now of adding CSM.
Sure,
And then you
sure.
saw the beginning of the,
Yeah.
so, and we now know for many 2Ps,
Yes.
both bright and low luminosity,
Yes.
there is a substantial bump, early bump. Now, what
Mhm,
else could
mhm.
cause this bump,
Okay.
except for a reasonable, amount of CSM that you can put?
Ask me at dinner. Simple explanation is CSM. That's what everybody's doing. So, but I mean, I don't think we understand the outer envelopes of these stars as well as the models tell us.
If there is a slightly longer rise at the beginning, could it be nickel in some way?
No.
Also powering
No, no way, no way. Not for these. Not for type 2P. No, no. No, there's no way there's nickel at the
And by
photosphere.
hand, maybe mix the nickel to the outside.
I have limits to what I'll do by hand. I will not put nickel at the photosphere by hand, okay? Sorry?
Even if you have no limits, you cannot do it.
Yeah, well, I'm,
Because you need too much, the luminosity is
Yeah.
You need more mass in nickel
yeah,
than mass that you can have in the supernova.
yeah,
You cannot do it.
yeah, yeah,
You
no.
have limits from the opacity on the amount of mass that you can have.
Okay, so let's get back to the real axis real quick, right? So we're now back on the real axis, okay.
Besides CSM, we currently don't have any other.
Right now, the only variable people have is CSM, but we know red supergiants are nasty, nasty, nasty beasts. At the photo, I don't have images of nearby red supergiants, but they're sure as hell not the star that's in a 1D model. We know that, okay? So we have to wait until we can figure out what to do about that problem. So I think some of this is premature, calling it CSM. In the conventional, it is circumstellar matter, but when you say circumstellar matter, I think most people think winds, right? I think there's lots of opportunity for, halos or coronae, or I don't know what the right word is.
Stuff outside the Mason model.
Stuff outside of a 1D stellar evolution model. Yeah, yeah, yeah. So we'll see. I mean, we don't have the answer. Sure.
So the correlation of nickel mass with explosion energy.
Yeah. You want to see this plot, or you want to go to the other one? This is kind of the same.
No, I guess it was nickel mass. You had the
Yeah.
football version.
Yeah,
of the
sure.
mass was the nickel mass.
Yeah.
I mean, that's a little bit surprising considering all the stuff one can do with fallback and core masses and everything. Is that correct? Or is that a surprise in terms of putting the bomb in the middle of the stars?
Oh, I don't think I can get all of this from shock nucleosynthesis,
Right.
if that's what you're asking. Yeah. I don't think anybody's tried that.
It's surprising.
Yeah. Yeah.
In the sense that if you just put bombs in the bottom of random stars, you wouldn't get
Right.
that.
Right. You don't get this. All I'm saying is the slope is correct for shock nucleosynthesis. Yeah.
The slope is right, but it would look a lot worse if you just put bombs in the bottom.
Yeah, you could look at the only paper that's done that to date is Tugg's paper, where they've tried to do some incorporation of the central core. And I don't know if they have a plot. They probably do of their models. What's this versus that? It would be interesting to see. It's probably in there. There's like 60 plots. I bet it's there. That would be the only one I know where somebody's tried to do both. I don't think anybody else has done it recently. Okay. All right. Okay. So now I'm going to totally switch gears and talk about supernovae that were detected. that are way brighter than type 2Ps. By way brighter, I mean a factor of 100 to 1,000. Okay? So let me just say it out loud, right? I've explained the luminosity. If now I show you a supernovae that's 100 times brighter, and you believe that formula I gave you, and you believe that the stars can't become a tenth of a solar mass, or the radius can't become 10 to the 4 our sun, or the energy can't become 10 to the 53 with the explosion, there's a problem. Okay? And these are the superluminous supernovae, and it was found, we invest a lot of money in big telescopes. This was found, the first best class of this was found by this little dinky telescope, ROTSE, so those of you who remember this history. It's too bad Avishai is not here. So this was the first paper that came out on these objects. It was Robert Quimby's thesis work. And so basically you can see here most luminous supernovae yet identified. It was typically a factor of about 100 brighter than the brightest type 2Ps. Okay. So in Quimby's survey, he had a number of these objects. So here's the best plot to show them. So at this point, this was early days, so this field's gotten richer. There's now 50 to 100 of these objects. But I like this plot from what Robert originally did. So this is showing days after maximum. A typical type 1A, he doesn't even have type 2Ps on here. Okay, they're sitting down here, minus 18 or below. So he's showing you a type 1A, which of course is powered by nickel. So remember the peak here is from nickel. It's about a solar mass of nickel to get that peak. The objects he started to talk about were, there we go, 2.5 magnitudes brighter. So this is a factor of 10 brighter than a 1A. So if you want to explain it with nickel, I have to have 10 solar masses of nickel. Okay, if that's what you want to do. So that's what these were. And the ones I'm going to highlight and talk about completely are are ones that back then we would call type 1C. They're basically objects with no hydrogen lines and no evidence for interaction. So in PTF and in pan-stars, these became minor industry. So this is the Robert Quimby's paper on a number of these events that were found in PTF. And there's sort of a beautiful detective story here, which I'm not giving justice to, and I don't know if anybody did. Did somebody talk about these? Nobody remembers them? I thought Avishai was going to do these. He didn't do them? These are his favorites. Okay, all right. So again, so we're up at minus 22. So I think it's important to go back real quick, because I have it right here, and go back to this plot. So these are the core collapse supernovae, minus 14 to minus 17. We're at minus 22. So that is a factor of 100. Okay? So here we go. So there's many of them in PTF. There were some old detective stories of weird events and other surveys, but typically they're between minus 21 and minus 22. You see they have a long duration, typically 100 days. They're found at high redshift, so all these things make it easier and easier and easier to get data. The redshift's a bit of a problem because it's further away, but the redshifting in time helps. Here's how they were also identified as a class, which is once you get the redshift from finding a narrow line somewhere, you could see the objects in this case were from 0.28 up to 0.5, and then this weird object that was in the Supernova Cosmology Project sample was at 1.2 was the redshift. I don't think these will be useful for cosmology, though others would argue with me. But let me just say that and then not talk about it again. But basically, you could start to see that there was a similar spectra from all these once you get the redshift, and you can start to see there's some shared spectral features, right? Which in this paper, which was the Nature paper, were identified as oxygen. I'm going to show you what Dan thinks it is. This is a nice summary of all the PTF supernovae. So this is from Avishai's group. These are the hydrogen-poor superluminous supernovae in this plot. So again, this is showing the magnitude at peak. Just look at the top plot. These are the number of events now that were in PTF. So it's 15, something like that. But they have a dynamic range themselves of about factor of 5, roughly, within. As you go to fainter but still quite bright events, you start to see what are called the 1C broad lines. Those are events where you see very fast-moving ejecta. And then these are 1BCs, which I'm not going to talk about. There's no real rate from this work because rates are really poorly constrained given how the PTF survey was done. So just to summarize this class of explosions before I launch into what at least a number of us think they are, this is where they sit. So again, core collapse are way down here. Here's type 1As, and these guys are sitting way up here. Okay, as I'll show later on, they're associated with high specific star formation rate galaxies, aka low metallicities. There's no hydrogen. They're 100 times brighter. And I don't know if there's a current rate that's better than this number, but it is important for what I'm going to talk about that the rate of these is quite low. So it's of order 1 in 10 to the 4 of the core collapse rate. Okay, and I think eventually this will get nailed. I don't know if anybody has an update, but if anybody's seen a better number than 1 in 10 to the 4. So they're rare events, but they're really bright. Okay. Yeah. 1/2000th. Okay, great. Yes. Well, the velocities aren't that well constrained from that until you know what the spectra are. So I'll show a little bit on the velocities. Yeah, I think I have a plot of velocities. Okay. So when am I supposed to be done? 12:15, 12:30? 12 you start question. Okay, great. Okay. So Dan and I got quite intrigued by these. I don't want to say it, nearly a decade ago. Sorry, Dan, we're getting old. And the hypothesis we pursued was that what we're seeing are a class of supernovae for which there's an internal power source that's not nickel, because the nickel masses would be kind of crazy. There's no evidence of interaction with material outside, and so we need something to power it from the inside. And the thing that we deem not crazy is to use a young, rapidly rotating, and highly magnetic neutron star. So we know in our galaxy there are objects called anomalous X-ray pulsars and soft gamma repeaters that we definitely understand as being highly magnetic, 10 to the 14 to 10 to 15 Gauss. We roughly know in our galaxy that 10% of neutron stars are born highly magnetized. So that I'd say let's call that a known thing. Okay. What we don't really know well from the galactic sample is what's the initial rotation rate. That's what we don't really know well. And so the hypothesis we made was that maybe some fraction of these are born rotating rapidly enough that the energy due to spin down could power these light curves. Okay? And so just to give you a number, if I'm highly magnetic and I'm born spinning at 10 milliseconds, I'll spin down in about a year. And that means over that time scale, the energy from rotation will have an opportunity to power the supernovae. Let's put it that way. And so if I want to do that, if I now go back to everything I've been talking about with respect to the ejecta, I want to reheat the ejecta before diffusion, before the diffusion time. So the simple algebra then is this is why we went to high magnetic fields, is that if I want to do it with before diffusion occurs, I basically have to have a high magnetic field if I'm spinning at 10 milliseconds. So the picture is I do a normal supernovae. What I mean by that is I have a shock wave go out, I have the ejecta expand, okay? And then I turn on a power source over time that is now going to send a new shock wave in from the inside through the already expanding ejecta. That's the calculation, okay? And we had a lot of fun with the analytics, and Stan Woosley also had the same idea at the same time. But the idea is that this is not asking too much. So remember, we're a part in 2000. Okay, I'll take a part in 2000. We're at a part in 10 here, so it's 1 out of 200 young magnetars are spinning at a rate to screw things up. That's what we're asking for. Yes, please.
Why should it speed so rapidly?
Yeah, so we have evidence of neutron stars that are born, reasonably rapidly rotating. The main problem in supernovae is getting angular momentum out. So if you don't have large angular momentum loss through the life of a star, you won't even get the core to collapse. So I'm asking for about maybe 1/10 of the breakup, something like that, and so it's not that rapid relative to it's not. I'm not asking for breakup. Breakup's a millisecond, just to say it out loud. Sorry, the breakup frequency is a kilohertz. Yep.
Why take 10 milliseconds? Shouldn't it be 2 seconds, 2 milliseconds, or 3 milliseconds?
Oh, there's a variable. Yeah, you'll see. Sure, it's a free parameter for this. That's right.
So does
Yeah.
does the time scale works out okay? Because for like a millisecond or whatever, it's like half a day.
Yeah. So the problem is going to be the following. I'll show the algebra, but let me say it because you've asked the question. So if I just dump all the energy in, let's say on the time scale of, let's use a day. If I do it on a time scale of a day, that's all just going to get lost due to adiabatic expansion. Okay? So if I really want to do damage to the light curve, I need to add the heat in at a late time so I don't lose it to adiabatic losses. Right? It's not that different, and I'll show you, than just having a bigger star. Okay? And so what I do is I use the explosion. So one way to think about it is I use the explosion to make a bigger star. Right? So I wait 20 days, it's expanded out, and then I reshock it. Okay? And so if you do it rapidly, you're not going to modify the light curve at all. And so there is going to be a sweet spot, as you'll see. When I'll show you the results of the analytics, you'll see that there is a sweet spot, and if you put it all in too soon, it doesn't help you at all.
But can you get such high field if you were around 10 milliseconds?
Oh, we have no idea. I mean, we don't understand origin of magnetic fields, so no. So yeah, I'm not worried because I'm not using all of them, right? Yeah, Udi.
Related to this question, actually, for me, it's a bit surprising that the fraction of highly magnetized neutron star with this rotation is so small. Because there are claims, but at least when people ask, how do I produce this magnetic
Right,
field,
right.
they say that you must have very fast rotation.
Yeah.
So it seems that this is true. Actually, one of the questions I had for a long time, where are all the magnetars? 10% produce 10 to the 52 ergs, where are they? So it's actually quite surprising. And if this is true, then we need a new model for how to produce a magnetic field.
Yeah.
How can you do it when only such a small fraction of the star rotates this rotation?
Well, yeah. I hear you. Remember,
The fraction of
this-
neutron stars born with a magnetar strength field in there is pretty large, at least order 10%.
we know that 10% are born with strong magnetic fields in this range. Is that what you're asking?
Yes, but how robust is it that you need them to be slowly rotating?
Oh, within our galaxy, the initial spins are only constrained by the fact that if they had a higher initial spin, they would have modified the supernova remnant they're in. So there's not, most of the objects in our galaxy are in a supernova remnant. They're young objects, so you can actually study the properties of the remnant. So if you had them all born in a millisecond, you'd have a problem with the supernova remnants, is the claim. That's the claim. I haven't done that, but that was the claim. Sorry? I can show you the paper. I can give you the paper. It's not my paper, but it's not just a claim, it's a paper. That's the honest truth, right? Yeah.
Have we seen any magnetars within or associated with the supernova remnant?
Yes.
That's how they're
That's how they're identified. Yeah, absolutely. Yes. All of them, the first approximation. They're only active for their early phase of their life, so they're still in a remnant. Yeah. Okay, so here's what I said it verbally. Let me just show you the formula. So the way one way to think of this is I said I'm going to take the R naught that was there, and now I'm going to have it be the velocity of the ejecta times the spin down time. So that's the effective radius of the object at the time at which I inject now an energy which has to do with the spin down energy. So this is just the energy of the pulsar. This is a half I omega squared. Right, here it is. And so I can modify this luminosity as long as the energy that was spin down is bigger than this formula, which is easy to do. So I can easily reset the entropy. All right, I can also then calculate the peak luminosity. It's the same algebra that we've all been doing. I very quickly get into the realm of what I need. So this is not a stretch. So what's it look like? So this is from the original paper that Dan and I wrote. So if I let the ejecta expand, so here's now the velocity. So this is a pre-exploded object. So this would be the velocity, the density as a function of velocity coordinate. So this is a Lagrangian coordinate. Because we're putting an energy source in the center, I sweep up the material in the interior and make a thin shell. But in temperature, you can see that as I have higher spin energies, higher 1/2 I omega squareds, I basically make the object hotter in the interior than it would have been otherwise, right? Here's the almost no energy injection. So I'm increasing the temperature. And again, this is just the fact that I've shocked all this material. This is for an ejecta mass of 5 solar masses, an original supernovae energy of 10 to the 51 ergs, and this is at 1 month. Okay? And this is a magnetar with a spin down time of a day, but it's a power law. Okay? So this is just the 1D versions. So here's what light curves will look like as a function of days since explosion. So here are the luminosities. Here's the temperature at the photosphere, and people asked about velocities. Here's the velocities. In this case, in a 1D model, the velocity asymptotes to a fixed value because of that thin shell. So if I go back to here, you can see that I've swept up all of the low velocity material that would have been moving at low velocities deep in the interior, has been swept up by the energy injection from that pulsar wind. Okay? And so I get a lot of stuff at a finite velocity. This is obviously Rayleigh-Taylor unstable. Okay? So back to this question of the sort of how Goldilocks is this? How much am I asking, right? So this is the, from the analytics, this is the time to the peak light on this axis. This is for a 5 solar mass, sort of a 1C scenario, versus the peak luminosity in 10 to the 43 ergs per second. So here's 10 to the 42 is here. Here's my boring typical objects. I'm cranking them way up. And then this is a function of 2 variables, one being the magnetic field strength. So this is 10 to the 14 Gauss, maybe 10 to the 13. Darn it, I don't remember. Here's a millisecond, 3 milliseconds, and 10 milliseconds. So if I'm highly magnetic, this is the highly magnetic line, and I'm rapidly rotating, I don't change the peak luminosity at all. That's what I talked about, the fact that you just dump the energy in, it doesn't do anything for you. If you really want to do damage, you want basically the spin down time to be of order of the diffusion time, and that's what this peak is right here. And at or near the peak, this is about as good as you can do. You inject the energy, you're at the diffusion time, which means the radiated energy is roughly the injected energy. Okay, so the best you can do is at this peak, which is when the diffusion time equals the spin down time. Okay, so Dan has a nice plot sort of reminding us of where these things sit. So now this is the light curve duration of these events. Here they sit. Here's ordinary core collapse. So this is again versus luminosity. So the ordinary core collapse supernovae are sitting down here. This is if I have balls of material where the nickel is a 10th the ejected mass or nickel's everything are shown here. And again, these events are sitting in a place basically where you can't do it with nickel. It would, it's just too much. It exceeds the ejected mass. Whereas the magnetar hypothesis gets you into this regime. Okay. This is for 1 millisecond for 5. This is the magnetar maximum. Okay. So how well does this do? Well, everybody knows now this has become a bit of an industry. The observers love it because we gave them formulae. They use the formulae. So here's an example of what happens. And the joke I always like to tell is, I guess this is old enough now that my daughter was much younger, but she looked over my shoulder one day and she said, and I said, "Isn't this plot great?" And she said, "Is the line supposed to go through the points?" A reminder that, yeah, this is really good for an astronomy, but to most of us, it's an embarrassment. Okay, there we go. So this is an ejecta mass of 5. This was the original supernovae energy. Again, you need that to get the ejecta out. Initial spin in this case of 1.5 and a B field of 2 by 10 to the 14. So this just keeps going. I could show you multiple examples, which I'm not really going to because I want to be certain I have time for more questions. Let me talk a little bit about the spectra. So this is the work that Dan did. That is in a paper with Andy Howell on a few events that were in the supernova legacy survey. So on the right, so basically there's a strong preference in this case for carbon and oxygen. So these are Dan's calculations with Sedona showing different possible compositions relative to a given supernovae. So he preferred this, and as a function of luminosity. So basically, the expectation is this material is carbon and oxygen, is the expectation. Not a surprise, given that it's 5 solar masses, right? So this is an object that's totally stripped. These supernovae, again, there's a lot of them now. They do prefer high specific star formation rate hosts, as do GRBs. So this is showing, this is from Lunan, from Ito's group. And again, this is, a lot of different groups have this now. So this is just showing as a function of the specific star formation rate. So what that is m dot over the mass of the galaxy. That's what this plot is. Showing for core collapse supernovae hosts, this is their cumulative distribution of where they are. But these events, these superluminous supernovae, are occurring in galaxies that aren't that different than long, in this case, long GRBs is what they were highlighting. But these things aren't following the normal core collapse population. Okay. Somebody asked about what are the spin versus magnetic fields inferred, again, from Avishai's group, this summary of all the PTF events. This is just the histogram. This is just the inferred. Let's just say inferred. I'm not going to say measured. For the hypothesis of explaining these with magnetars, here's the resulting inferred magnetic fields and spins for whatever, a dozen events that were in the PTF sample. Okay. Oh, this is from fitting those formula. It's basically just putting a light curve. Yeah. So to get, I kind of breezed through it, but you play this game basically, and you infer a spin down, and these are just assuming dipole spin down formula. Okay. So, yep. Okay. Thank you, Sturl. These are all stripped for everything I've shown you so far. And I'll close with the unstripped. Thank you. I'll take that. Yeah. Okay. So I think the mistake, I'll take blame for it. We called them magnetars. There's many people who are upset with us because we called them magnetars. So these are magnetized neutron stars with fields of order 10 to the 14 Gauss. That's the problem, right? I mean, yeah. So that was that's just a, okay. Did I answer your question? Yeah, I mean, okay, so we learned this. Basically, here again, I'm using magnetar powered, which is probably a bad idea. But all of these are in 5 to 8 solar masses. So a natural question, sorry, let me show one more plot because Ken's here. So one big uncertainty, and if you have any questions, raise your hand. Huh? He doesn't. So there is some work on the 2D, and there's been some work on the Rayleigh-Taylor instabilities, which we'll see how it plays out. Okay, let me go back. So Sturl asked, what about this same exact hypothesis, but in a red supergiant, basically? Why not? And I totally agree. There's been 2 recent papers on that hypothesis. I'm going to highlight the paper by Luc Dessart and OD, I would presume. I'm not sure. I don't want to call it audit. That's a terrible last name. So it's probably OD. This just came out mid-December. So this is a single red supergiant model with whole different values of magnetic field and spin, et cetera, et cetera. But this is what they find for those events. So this is what it would have been. Typical type 2P, remember, it would have been 100 days. So it would have only lasted 100 days and sat here. Unfortunately, they don't have on this figure the one with no power source in the interior, but it would have been boring and down here. Okay, so they're brighter, again, no surprise, and much longer. Okay, so this would be one with hydrogen. And this is why it's really too bad Avishai is not here. We'd have no. These were pretty big. These were well. They play with the spin. They play with the spin. Yeah, they play with the spin. So you may remember Avishai had this statement about, what was it? Blue supergiants could be type 2Ps or something. I can't remember what it was. So this is the figure that everybody needs to send to Avishai. So this is in this paper by Desart, and this is my final figure. So this is showing 87A. Right? This is the nickel in 87A. That's the nickel tail. This is the luminosity of 87A. Okay? There's an event that was highlighted in the Desart and OD paper. Ogle SN14073, which is not a supernovae I was familiar with. There are a lot of them, so I don't have to know them all. For which this is the light curve. Now, you may remember there were some that Avishai showed that were kind of like this, but I don't know what the luminosity scale was. Okay. So this is a type 2P, has hydrogen, lasts 150 days. Okay. They model this from what I just talked about. They put a magnetar into a red supergiant. And this is the resulting calculation on top of the data. If you wanted to explain this tail as nickel, you'd need nearly half a solar mass of nickel. Rather, they're explaining it as the residual of the spin down of the highly magnetic neutron star. Okay? So what's interesting, I think, about this work is that it may be, I mean, Avishai said there were a few type 2P things that had this weird rise of about a factor of, almost 2 is what he was showing. And so what I don't know is whether it'd be good to lay hands on those and see if they were less extreme examples of this one. Okay? So on that point, I'm going to stop. I'm going to talk about what I didn't talk about. I'm just going to put up what I didn't talk about, and I'll take questions. So thank you.